Okay, so this is lecture 17, and we will continue our discussion on PLL building blocks. And the next one is charge pump. So let me just draw a simple block diagram of a charge pump plus PFT, because PFT gives you the control signals for the charge pump. So I have R, V, so the all discussion about charge pump is mostly how to design the current source and how to place the switch, and what are the consequences of whatever you do in the design. So this is up, down, I see, let me write it as I up and I down, and this is the current which goes into the loop filter. Okay. So the signal control for the charge pump R. So let me just write with respect to the PFT input. You have R and V, and I am just plotting it right now at that locked state. So up, there is some reset time which we need to have in order that any of the switches which we are using, the switch should become active. Okay, down, and ideally if ICP and I up and I down are equal, then the ICP, small ICP, or the current going into the loop filter is actually 0. Okay, so this is an ideal charge pump, and this is only means ICP is I up minus I down. Okay, and the period for which both the switches are on, that is T on, and the reference period of at which the charge pump is clocked is TR. So this is an ideal charge pump. Now let's start with the thing what all can go wrong in this ideal charge pump when you implement it as a real charge pump. And the very means I can just give right now, I will just show you what a real charge pump can be. It's nothing but I am replacing the switch with the MOS switches and replacing the current source with the, let's say I replace it with the PMOS current source at the top. So this is VBP, and we will go into the design of this in a little bit some time, but this is just to show you where all things can go wrong. So this one is down, and because it's a PMOS, so this will be up bar. Okay, so M1, M2, M3. Whether we are going to use the design or not, we will see that later. But this is the easiest replacement for the ideal block which I have just shown you. Here M1 and M4 are switches, okay, and M2 and M3 are current sources. Okay. So let me ask you what all things can go wrong one by one. So what do you think the first one can be? Mismatch between, okay, very, be specific on this part. Mismatch between up and down, or mismatch between up and down current? I will see the difference. Huh? Okay, so what you suggest is there will be a mismatch between I up and I down. Okay, that is one thing which we can have, which means the current sources, they are not equal. I up is not equals to I down. What is the next thing you think can happen? So you see your up and down pulses, they are coming from a PFT, And right now I assume that up and down are equal. They should be, because that is what we want, and we will try our best to get that T on is same for both up and down. So what other thing can go wrong? Timing errors, how? Or dynamic errors. So you are a step ahead of this. What you say, dynamic errors arise because of what? Maybe a parasitic capacitance at all the nodes. What these voltage settle to initially and what these voltage have to be in a settled state. Right. So this is a system which has to be reset every reference edge. So the potentials will vary. That will be dynamic errors. So so mismatch between I up and I down is actually nothing but static errors. Let me just put it that way. Right? Because we have a biasing voltage and everything, and there we are not able to have I up equals to I down. That comes under static errors. The other one, what you suggest is a dynamic error, and these dynamic errors means it can be because of the parasitic. This is like the charge sharing can happen. Charge sharing during transient. This is one thing which will cause you the errors. Then what you can have a clock feed through, because all up and down are periodic signals which are, yeah. Yeah, what are the exact reasons behind the static errors? Let me put that question to you. VT mismatch, W. Yeah. So means, let me just say, how will you generate VBP and VBN? Through some diode connection, right? Now, what is the ratio between the diode? That is the mismatch which will come through. So I up equals to I up not equals to I down is the result of. So let me just, again, this is slightly deviating. Let's say you are having a single current source. You push in a diode, you get an NMOS current source, right? And this is the current source which you would like to mirror it in your basically transistor VB. So I'm calling this as VBN, right? Then because I want the same I naught current, I will push this current source. This is a very let me just call other way of brute force way of getting the current source. So I will have this as I naught, and PMOS will also current, so I can generate VBP like this, right? And I will give this VBN and VBP to the current sources in the charge pump. There will be a mismatch between. So this one is nothing. Let me just name this as M2 dash and M3 dash. Between M2 and mismatch between M2 and M2 dash and M3 and M3 dash will cause you the static errors. Okay. That we can do it. Means the bottom transistor is a transistor where the control voltage Dn, if it is in like operating case, that is 1. So we can just put a switch. That is not that difficult. This is VDD, right? So that part we can take care of. Now the thing is, what is the mismatch, like the VT mismatch and the W by L, the area mismatch. So the other thing which static errors can also be at what is the output control node. You will see a channel length modulation, right? So unless you mirror that channel length modulation back into the charge pump, then there is a way how to do it. Otherwise, you will see the channel length modulation effect also. But overall, both mismatches, whether it's a static error or the dynamic error, they are causing us to have I up not equals to I down. Okay. What other thing can cause any other thing which you think is possible? So you are having an up pulse and down pulse, and up is going to the PMOS and down is going to the NMOS. delay between means the is a kind of an input to output delay, right? So when you give the up pulse, whether the PMOS switches on at the same time or as the NMOS switches on, so those delays will also lead to a different current at the output. So let me just say uh, up bar and down to I out delay. Uh, yeah, let's just call this as I out, which is I up and I down delay. Okay. So those things can happen in the charge pump. And let's look at if these things happen, like you have a mismatch in the current, what is the effect on the charge pump PLL? So let's start with the first one, that mismatch. Sorry. So we will look why these mismatches arise later. First, look at what is the effect of these mismatches. Mismatch between I up and I down. Okay. So let's say, let me right now only plot up and down so that we can just, so if I have up and down of the same pulse T on, in that case, which I wanted ideally, in that case, and now let's assume that I up is greater than I down. Okay. So if I up, or let's say I down is greater than I up, then you will have a current like this. Okay, let me just make it a little bit bigger. Okay. And this is equals to I down minus I up, given that I down is greater than I up. There's nothing special about it. I up can be greater than I down. Okay. So this one is ICP. If this is the profile of the charge pump, what do you think will be the case in the locked state? Because if it is always giving you a think about it, if it is always giving you a negative current pumping into a capacitor all the time, like every reference clock, that means the capacitor voltage should go down in a steady state. And if it goes down in the steady state, you will not be in lock mode at all. So what should happen if you want to lock this? Negative feedback loop will take care of it. But how will this change the up and down signals? That should lead for some time, which means that in locked state, the up and down signals will have actually an offset. They will not lock to a zero offset POS. They will not lock to a zero offset thing. So in locked state, your up and down signals in locked state, okay, which will then give you ICP as high for the time when up is high and low for the other time. Okay. And then this is going to repeat every reference period. So what we have here is this is I up and this one is I down minus I up. So can you tell me what, okay, so this time period is also, this is T on, oh sorry, this is T offset and this one is T on or T reset period, whatever we have. So let me just call this as now as a T reset period. So let's change this to T reset because that helps understand the PFT behavior. Okay. So if I ask, without doing any whole of the PLL analysis, what should be the log state? Can you tell me? In a steady state, area of both should be combined area should be equals to 0 because in a steady state we do not want the control voltage to change, right? So what that means is that this region should be equals to this region. Okay. So the condition is that I up into T offset is equals to I down minus I up into T reset. Okay. So you have this one is, so let me just write it as T offset by T reset is nothing but I down minus I up by I up. And I'm just now writing this as delta I by I. So you get an offset period which is proportional to the mismatch in the current. Okay. Now I can write the same, this is T offset. I can also write this as a phase offset in log state. It's nothing but 2 pi times T offset by T reference period, which is 2 pi into delta I by I. Now this is equals to T reset by TR. Okay. So you see that phase offset is dependent on your delta I and the reset period also. It's a function of that. If your delta I increases, then your phase offset increases. Okay. He's telling that this was, is there anything wrong in the equation? Let me just see. I up into T offset is I down minus I up T reset. The area is fine. Reset. This is I down delta I by I up. So T offset is this. Phase offset should be, yeah, this is the phase error, which is T offset by TR. And T offset is, okay. So this is fine. Where, let me just write that this is a reference period. Okay. So now this current is pumped into, let me just start right now with the means I am right now not, sorry, let's say right now we are not considering the other capacitor of the type 2 PLL. C2 right now let's not consider, so it will be easier to understand. So I have ICP going into the loop filter, and this is a control node, P control. Okay, so what do I have at ICP in logged state due to mismatch? So ICP is something okay, so this one is ICP. In response to ICP, when you only have a single resistor and the capacitor, so what you have, V control T. So what should be V control T? Oh, what has happened? Okay, come back. Okay, so let me just say V control T is, yeah. So what should be V control T as such if ICP is of this profile? So it should increase. There is no change in the capture voltage in the beginning, right? Means it's surely dependent. This thing, the caps means this node will basically rise from zero and go to ICPR in the end, right? But ICPR that will have a jump. Okay. So we have V control T will be this. Okay. Yeah, with C2 it is a different case, right? No, we are talking of only this resistor and a capsule right now, R and C1. Yeah, yeah. Here I am showing is a very much like this is majority will be like this. So if you want, let's see that if anything. Oh, sorry, yeah, exit full screen. So what we have here is ICP is equals to V control. So forget everything. Just look at this. ICP is equals to C1 times dVC1 by dt. Right? Do not have C2, and the control voltage here V control. Let me just call VC1. That's will be easier. This is VC1. So VC1 is going to rise, right? And in response to VC1, what you have is, so let me just write, VC1 is equals to 1 by C1 ICP times T. This is constant. And just look at the constant right now. VC1 goes that way, and your V control is actually your 1 by C1 ICP times T plus your ICP times R. This is the other part is the integral part. So on top of this, you can say what I am having because of the C1 is something because of the C1 part. I hope that is right. Now, so in case you had C2, what will be the case? So let me just use the same color so that, so in case you have C2, then you will not see the jump. You will see it might be rising here, right? And then it will rise low. Okay, that's the negative current. And then when you do not have any ICP, this whole RC1 actually acts as a discharge path for whatever voltage is there. So you will have, means you have to do the charge conservation over the whole cycle in case you have C2. So this one is with C2. Okay, so let me just, we will take the effect of that later, but let's just consider we have only R and C1. Okay, so because of the resistance here, you have ICP times R ripple, ICP times R. Okay, now, so let's see what happens at the control voltage. V control okay, let me a little bit make it lesser. Okay, so this actually can be divided into two signals. Let's say VA, okay, and this one is VA, and the other signal is VB. I am doing it, I will tell you. So this consists of two signals, VA and VB. Okay. So if I ask you that V control, which is equals to VA plus VB, what do you think? Which means we know that this is surely ICP times R, right? And this variation is delta I times R. Okay, if you're making a good design, then delta I should be much lesser than I. Okay, now think about it. If you find the effect of V control at the output, that can also be found with as a superposition of VA and VB, right? And VA is much larger magnitude here as compared to VB. So for now, we just focus on what the VA is doing rather than VB, but this is totally combined effect of these two. And VB I am right now just neglecting it here because it's a very small value spread over a long time. Okay. So now V control is equals to VA plus VB, which I am approximating to VA only. Okay. And this VA can be written as, now you see that this is periodic with reference period, which is an cos n omega r times t. Omega r is reference frequency. So, and this period is t offset, and the whole period is a reference period. Okay, okay. So can you just quickly tell me what is A naught and AN? So A naught is how much? Yeah, which is ICP, or ICP I'm treating as the same as I times T offset by TR. What is AN? So let me just verify it here. So I have for AN, I will do the Fourier series calculation, which will be integral of 0 to TR times this magnitude is 1. So ICP times R, okay, into cosine of m omega r times t dt, which is equals to, this is only finding the an cos n omega r t and cosine of m omega r t dt integral 0 to here. Okay, so what I have from here is ICP r, and cosine goes to sine, so you have sine of m omega r t. So okay, this one is 0 to t offset, because that is 0 otherwise, which is equals to, now n should be equals to m in order to find the Fourier series. So what you have is an by 2 times, I think this all you all remember, this will be 1 minus cosine of 2 m omega r t dt 0 to tr. So which will be an is equals to, or am here, so let an or am, that's fine, 2 ICP r, okay, here it should be m times omega r by n omega r. Okay, sine 0 is 0, sine of n omega r t offset. Okay, so just let me write it as ICP times r. Okay, let's keep it this way only, n omega r into sine of 2 n pi t offset by tr. Okay, so Now I will just write V control. So you see there are all the harmonics here, but I am only will talk about the first harmonic. If you take all the harmonics and then so what happens with the V control? So this V control goes to an oscillator and output V out, and you have V out is equals to some amplitude. So let's start, keep using the cosine of 2 pi kVcu into V control dt. Okay. Now, if you consider all the V control means you consider V control with all the harmonics, that will become a complicated function. So right now, you can do that and find what the magnitude of the higher harmonics are. But let's consider only the first one. So A cosine 2 pi kVcu, and we have to assume that there is some DC value. So let me just write at V0 the free running frequency or whatever the required frequency for the locking. Now here, if I write V control with only the fundamental, right, that is AN is your, yeah, this is what we find as 2 ICPR by omega R, N is equals to 1 for N equals to 1 into sine of 2 pi T offset by TR times cosine of M omega RT, or this is omega RT. Okay, yeah. What am I considering? Yeah, so you will find that the sine term will be 0 here. And this, when you're only writing the Fourier series of this part, you can find that. Okay. So, and even if there is a sine term for, like, if I take these two waves, right, the positive and the negative VA plus VB, you will find definite sine term, and then you can club it in some phase difference. So it will be, so the whole idea of doing this is that you find something periodic in the control voltage. How does that period, and it have with some magnitude, so how does the magnitude and the periodicity in the control voltage is going to change your output spectrum? Okay, so if I start doing all the sine and cosine, I think we will be lost in the sheer maths. That's the thing I am still trying to avoid. Okay, so now see, again I am making an approximation here that sine of, in order to keep it still simple, this is 2 ICP R by omega R, and this I say is sine of theta is equal to theta. Okay, and if I just write this term as a phase offset, then 2 ICP R by omega R into delta phi offset time cosine of omega RT. Okay. So now I have 2 ICP R by omega R, okay, into delta phi offset time cosine of omega RT. So this whole is now the new control voltage. And the second part is just coming because of the mismatch between I up and I down. And the information about the difference between I up and I down is in delta phi offset. Okay, so just, pardon? Okay, so whether 2 pi is before KVC or not, that very much depends whether I am using it as a KVC as a hertz per volt or a radian per volt. So, okay, let's keep this as KVC is in units of radians. Radian per second per volts. So, this one, okay. Now, let's say this part only gives you the free running frequency or the locked frequency. What happens due to the other one? Cosine of omega naught t plus 2 ICP r by omega r into delta phi of set times kVco into cosine of omega r t dt. Let me see if everything is fine. Cosine of omega r, m is here. Okay, that is fine. So now again, so let's say this part is beta. So what you have is a cosine of omega naught t plus beta by omega r times sine of omega r t. Okay, this is another integration I did. Now this will be a cosine of omega naught t into cosine of beta by omega r sine of omega r t minus a times sine of omega naught t times sine of beta by omega r times sine of omega rt. Okay, if there is anything wrong because we are writing so many equations, just let me know, which is, there might be some plus minus here there. So now this term, so okay, so now I assume that this value is very close to 0 or very small. So this one is a sine of cos of omega naught t minus, so cos 0 goes to 1 and sine theta goes to sine theta. Omega naught t times beta by omega r into sine of omega rt. Okay. Now this is cos omega naught t minus a by 2. Okay. And sorry, a by 2, yeah, beta by omega r. Okay, so this I am right now directly applying the identity cos of omega naught plus omega r t minus cosine of omega naught minus omega r t. Okay. 2 is like minus 2 sine A sine B is equals to cosine of A plus B minus cosine of A minus. So just apply that identity here. So what we have, if I just rewrite it, so this one is A was there, beta by 2 omega r times cosine of omega naught plus omega r t minus cosine of omega naught minus omega r t. Okay. So what do we have? Initially, so let me just make it as I have, so I had only one tone at omega naught. But because of this mismatch in the current, it results into two other tones. One is coming at omega naught plus omega r, other is coming at omega naught minus omega r plus omega r. So let's say this is all in omega because we are dealing with omega. So, and this one is omega naught minus omega r. What is the magnitude of that? Magnitude of that is equal to uh, this magnitude is equals to beta by 2 omega. Okay. And what is beta? So where does the beta go? Where did I define it? Beta is defined here. So okay, now let's see. Beta by omega 2 omega r is equals to, okay, this one, right? 2 ICP times R by omega R into delta phi OS into KVCO into 1 by omega. Yeah, by omega delta phi VCO by KVCO. Okay. And beta by 2 omega is this. So let me now start. There was pi initially there. Where did the pi go? Oh, where did the pi go? Oh, I am writing as omega, so there is no pi as such. Yeah. Okay. So this one, now let's start writing as omega r times, this is 2 pi delta t, sorry, 2 pi t offset by tr. Okay. And 1 by 2 omega r is nothing but 2 into 2 pi by tr, and you have KVCO. So you see there's something will cancel out, 2 pi by tr, 2 pi by tr. So you have ICP r by omega r times T offset times KVCO by 2. Okay. Now this is the magnitude which you will have. Now we need to see how the PLL loop bandwidth and other things play a role here. Okay. So for that, now let me just write the loop gain of the PLL, open loop gain of the PLL when you are only using a type 2 PLL without the second capacitor, type 2 order 2, which is ICP by 2 pi into, this is combined PFT plus charge pump, into 1 plus, this was, the loop filter was R plus 1 by SC1, okay, into KVCO over S. This was the case, right? Which is ICP by, so let me just write it as CP by 2 pi into KVCO over S C1 into 1 plus SRC1 by, okay. So the Bode plot for this loop gain is minus 20 dB per decade, and you have something kind of this, which is, this is omega z, and omega z is 1 by RC1. So at frequencies much higher than omega z, now this is an assumption here, means how high it all depends. At frequencies much higher than omega z, we are considering that omega u is much higher than omega z. Okay, that means loop gain evaluated at omega u is equals to ICP by 2 pi KVCO omega u C1. Okay, well, let's just assume this so that you do not get into J factor, and this one will be R C1 as a cancels out. Okay, so I'm just finding at this one, and this should be equals to 1. So your omega u is equals to ICP R times KVCO by 2 pi. Omega u, C1 cancels, R is there. Okay. This is again considering that you do not have a C2 capacitor. So why I did this? Because I am going to relate this back to here. ICP R KVCO by, so let me just write it this as ICP R K VCO by 2 pi, okay, into TOS by T times TR. Omega R is 2 pi, sorry, omega I is 2 pi by TR. Is there any factor wrong here? I'm just wondering. It should not be. Okay, let's see what happens. By 2 pi. So this one is equals to your F bandwidth, or better, let me call this as, okay, this is fine. So omega u, right? I need to replace that. So this one will be, so what should this factor should be in terms of bandwidth? Omega u, which is 2 pi times f bandwidth, okay, and 1 by tr is nothing but this is 2 pi fr, okay, and then you have TOS factor. I feel there's something missing here actually. So let's just see that. What did we do? Pardon? Is beta wrong? Uh-huh. Yeah? Uh, no, I didn't get it. Right. We took the entire term as beta by omega r because the integral of cos omega rt. Oh, I didn't divide by omega r. So, okay, let me get it. No, there is this 2 omega r, right? Okay, let's see that. I think there's something. So we started from here, right? We control this expression is right, okay, and this expression should be right. I mean, I do not see anything because this expression is coming from sine omega. Yeah, so this expression is an is right. If an goes right, then you have t pi sine of theta is equals to theta, that is giving me 2 pi TOS pi r, that is delta phi offset. So this one is right, okay. I substituted 2 ICP by omega r delta phi offset cosine of omega rt, right? Now 2 ICP r by omega r delta phi of offset k VCO I am putting as beta, right? So that integral is cosine by omega r, sorry, and this should go right, beta by omega r. Yeah, I think that means there might be something else, but let me just get it here. 2 pi delta phi offset is T2US, that is also okay. 2 pi 2 pi. So okay, so let me just rewrite it. So this one is fine, 2 pi FBW by 2 FR, okay, into TOS. Anything else missing there in this expression? Nothing, right? It's not dimensionally correct. So what it should be? Okay, let's see that. Okay, I think let's end here this class already. I will check what the dimensions are. Okay, so let's stop here and we'll look next class.